Today we're going to look at three aspects of the magnetism of small particles. First, that when a magnetic particle is below a certain size, the particle will contain only one domain. So there'll be no domain walls present. Second, we'll look at how the absence of domain walls affects the hysteresis. How it leads to a particular magnetic response to a magnetic field. And then finally, we'll discuss a phenomenon known as superparamagnetism, which describes the phenomenon in which, when the particles are too small, then the hysteresis is lost completely. Okay, so let's start with the first one, the fact that a small particle is single domain. So we can understand this first just very hand-wavingly, because we know that a domain wall has a certain width. And in particular, the width of a domain wall depends on a balance between two contributions to the energy, between the exchange energy which prefers to have a wide wall. If we have a large exchange energy, then neighboring spins, neighboring magnetic moments prefer to be parallel to each other. They don't like to change their relative orientations, and so the domain wall tends to be wide. And the anisotropy energy, specifically the magnetocrystalline anisotropy energy, which is the energy that tends to orient the spins along a particular crystallographic direction. It means it costs energy for the spins to rotate out of that direction, and so this prefers a narrow wall. A large magnetocrystalline anisotropy energy will favor a narrow domain wall. And for typical ferromagnetic materials, for example iron, this competition leads to a typical domain wall width of around 1,000 angstroms, 100 nanometers. And so if a particle is smaller than that size, then a domain wall can't fit, and so it won't form. one can be a little more rigorous and look at the energy balance between a small particle that doesn't contain a domain wall and a small particle that does contain a domain wall, and think about which would be lower energy in which regime. So if we look at a small particle with some magnetization M with no domain wall, then this particle has an external magnetic field. Oops. And as a result of that external magnetic field, it has a high magnetostatic energy. This is the energy, for example, that allows a bar magnet to pick up to pick up something magnetic because of its external magnetostatic energy. It doesn't, of course, have any domain wall energy because it doesn't have any domain walls. If instead our small particle has a domain wall, then it has two regions of opposite magnetization, and so its external magnetic field is much smaller, and correspondingly it has a lower magnetostatic energy. But now it has a domain wall, and so it has a higher domain wall energy. And so let's think about, as a function of size, where this crossover between the relative energies of these two situations might occur. Well, the magnetostatic energy depends on the volume of the particle, and so it's proportional to the radius cubed, whereas the domain wall energy depends on the area of the wall, which is proportional to the radius squared. And so if we sketch these two contributions to the energy as a function of the size of the particle, as a function of the radius of the particle, then the energy of the single domain particle is increasing as r squared, as r cubed, whereas the energy of the multi-domain particle is increasing as r squared. And so we see that there's a crossover at some critical radius, which is again, as we said earlier, around 1,000 angstroms. Good. So we've established then that for some certain size, we would expect that the lowest energy configuration for a magnetic particle is for it to be single domain. Now let's have a look at the second point, which is the hysteresis. In small single domain particles. And we're particularly going to consider the case of particles which have an elongated shape so they look like this. And the reason for this is that the shape anisotropy tends to make the magnetization lie along the long axis. So our magnetization will naturally be oriented in this direction along what's called the easy axis, because this configuration has a lower magnetostatic energy than the magnetization oriented along the short axis of the particle, which is therefore called the hard axis. You can see this naively if we just draw north and south poles associated with the magnetization. In the case where the magnetization is along the long axis, there's not very many north and south poles at the surface, so there's not a large magnetostatic energy. Whereas when the magnetization is oriented along the short axis, the hard axis, we have many north and south poles. Of course, this is hand waving again at the surfaces, and this leads to a large magnetostatic energy, and so it's unfavorable. Okay, so then let's think about the mechanism of magnetization reversal in such a particle. So we start off with the magnetization lying along an easy direction. So let's say it's oriented to the right, and then we're going to apply the magnetic field in the opposite direction. So we'll apply our magnetic field to the left. The particle can't respond by domain wall motion because there are no domain walls. And the only way the particle can reverse its magnetization is by rotating the magnetization through the hard direction. And so the magnetization would have to then rotate through the hard axis before it could reorient to the opposite direction from where it started, which is the direction parallel to the applied field. And of course, the magnetization doesn't like to do this because there's a large anisotropy cost for the magnetization to lie along the hard axis. So let's have a look at what this does to the hysteresis. So we're going to plot the magnetization as a function of the applied field. And we're going to indicate field pointing to the right on the positive x-axis and field pointing to the left on the negative axis, and magnetization pointing to the right will be on the positive y-axis and magnetization pointing to the left on the negative y-axis. So we start off with our particle magnetized to the right. That was our initial condition over here. And so our magnetization is in the right pointing direction, and even with no field, it's still pointing to the right. And then we apply our magnetic field to the left, and as we increase our magnetic field in the left direction, our magnetization remains pointing to the right because it's very expensive for it to rotate into the hard direction. And only when we reach a very large field pointing to the left will the magnetization switch, and it'll switch very quickly at this coercive field because it really doesn't like to have its magnetization oriented in the hard direction. So it'll switch very quickly to the opposite orientation, which is the magnetization again in the easy direction. So there's very little range of magnetic field at which it'll be in between these two opposite orientations. Now we can remove the magnetic field or reduce the magnetic field in the negative direction, and even start now applying it in the original direction again. But once again, the magnetization hangs on to its new orientation until we reach this large coercive field in the positive direction again, and then it'll switch back. So we see that the shape of the hysteresis for a small particle containing a single domain, when the magnetic field is applied along the magnetization direction, is we get a very square and often rather large, in the sense that we have a large coercive field, hysteresis loop. So we have a large coercive field, and often with a large magnetization, because the particles are fully magnetized with no domain walls. Now, all this applies only if the particles are below the critical size for which they're a single domain, but above the size at which they undergo a transition to the superparamagnetic state. So the last thing we'll discuss is the phenomenon of superparamagnetism. And so if I plot the coercive field as a function of the particle diameter, what we've been discussing has been a region of small particles which are single domain and therefore have a large coercivity. If we go to larger particle sizes, the coercivity will generally drop off as our particles become multi-domain. But if we make our particles too small, then the coercivity actually drops to 0, and this region here is the superparamagnetic region. And so below a certain diameter, the coercivity is 0, and the reason for this is that thermal effects are strong enough to reorient the magnetization. And this we can understand because the anisotropy energy which provides the coercivity this is the energy cost of rotating the magnetization out of the easy axis and through into the hard axis. This is proportional to the volume of the particle. In fact, it's actually equal to what's called the anisotropy constant, capital K, times the particle volume. And we see immediately that as the particle gets smaller, as the volume goes down, the anisotropy energy goes down. So the coercivity, which is required, which is holding the magnetization along a specific direction, is reduced. And eventually, with small enough volume, of the particle, this anisotropy energy will become more or less equal to the thermal energy. This is now little k, the Boltzmann constant, times T. So the anisotropy energy is approximately equal to the thermal energy. And when this happens, the thermal energy can then spontaneously reverse the magnetization direction. Even in the absence of an applied magnetic field. And so in this regime, the thermal energy flips spontaneously the magnetization. There's no tendency for the magnetization to be oriented along one particular direction or the other. And so it's behaving like a paramagnet, like a non-magnetically ordered system. Of course, the size of the magnetic moment is the size of the magnetic moment of the whole particle. So it's very large. It's like a paramagnet with a giant magnetic moment, and hence the name superparamagnetism. So that's it for today, and thanks for listening.